All right, everybody, welcome. We are using Collaborate this week, and we are going to be doing an assessment as to whether we want to stick with Collaborate or we stick with Teams. And that survey will happen this upcoming weekend, and that will carry us through to the end of the year. A couple of questions have come up that I want to address for everybody. In terms of the lab, there are 2 quizzes now rather than just one. There is both a multiple choice quiz and a short answer quiz, and both of them need to be completed as part of the lab program. Yes, this is more than what you had in Chem 100, where you only had the multiple choice, but that was a conscious decision because we were unsure with how the Hayden McNeil website was working, but also to start off with something simpler, multiple choice, and now it's expanding so that the expectations on you to answer multiple choice and short answer questions it's increasing. So we're kind of putting a little bit more onus and responsibility on you. And the students who have talked to me about it have said that while it does take a little bit of time, labs do, it does really help them understand what they're actually doing, because it's not just guessing through a multiple choice exam. The problem set quiz, just as a reminder, you're not handing in the problem sets, but there is a quiz after each problem set, and the first quiz on problem set 1 is opened up today. It's on the Hayden McNeil website in the very first folder, Chem 101 problem set quizzes. It's in there. It is open Monday, Tuesday, and Wednesday, and you have 45 minutes once you start that quiz. One attempt, 45 minutes, anytime within the next 3 days. So Monday, Tuesday, and Wednesday. The other thing I did on the Hayden McNeil website, because I didn't realize it wasn't there, is I activated the calendar. So now on the right-hand side, you'll see a calendar, and that calendar has, right now they're pink, little pink blotches. Whenever there is something that is happening relevant to you, a quiz is opening, a quiz is closing, is what is presented in that calendar. And yeah, that's generally the announcements that I have for that. And we are going to work our way through the rest of this material using Collaborate here. So, to remind you of where we were last day, is we were here. We were looking at a reaction Were we? Yes, we were. Sorry. Right. We were 10:30. We're looking at that mechanism, the reaction, the decomposition of ozone to oxygen. Sorry, I lost my train of thought there. And here we had a 2-step mechanism. The first was the decomposition. My apologies. Shut off. The decomposition of ozone to produce oxygen and atomic oxygen. That atomic oxygen is an intermediate. It is produced in one of the reactions, and it is consumed in this case, the second reaction, whereas ozone is another ozone molecule reacts with atomic oxygen to produce 2 oxygen molecules. And we sketch this reaction coordinate as presented here. And yes, there we have the reaction coordinate, and that's where we ended off. Here's another reaction, slightly more complex. It proceeds via a 3-step mechanism, and what you can see here is that, excuse me, iodine must first break apart to produce atomic iodine. So molecular iodine produces atomic iodine, and then that atomic iodine reacts with hydrogen to produce another intermediate, IH2, and then atomic iodine reacts with IH2 to produce hydrogen iodide. The overall reaction, adding it all up, is what we would normally write. Hydrogen plus iodine goes to 2HI, but we can see from this mechanism that the intermediates are atomic iodine and this IH2 radical. The other thing that one could see in the context of control is if I wanted to speed up this reaction, it probably would be sped up if I could produce a good amount of the iodine radical. So if I were to use an ultraviolet laser to break apart iodine, so have iodine vapor that's present there, and then use a laser or a pulse of light to break it apart to produce a whole bunch of iodine radicals, then this reaction should speed up. And actually, very much, it does speed up to the point of actually reacting quite explosively. So normally it just happens slowly. It doesn't, at room temperature, it can happen very fast when you flash a light at it. So this takes us to the idea of now looking at catalysts. What is a catalyst? Does anyone want to tell me what a catalyst is? And similarly, what an inhibitor is? Please? What are the features of a catalyst? Speeds up a reaction. Good. Excellent. Decreases the activation energy without being used. So something that speeds up a reaction without being used up, it doesn't actually decrease the activation energy. Doesn't lower the activation energy per se. You call it lowering the activation energy, which isn't exactly correct. What is more accurate is a catalyst is something that increases the reaction rate by providing an alternate lower energy pathway. The uncatalyzed pathway is still there, but we're providing a new pathway as a result of the catalyst. And furthermore, the catalyst is itself not consumed. And put it all through there. An inhibitor binds to the substrate, and an inhibitor, as its name sounds, slows a reaction by blocking the lowest energy pathway. Somehow it stops a reaction by blocking the lowest energy pathway. So that is catalysts and inhibitors. And that kind of takes us to a demonstration. I need someone to tell me if you can actually see me, or has this camera frozen again? Can you see my hand waving?
Yeah, I can see.
Good, thank you. I just need to put on some protective gear, and while I'm doing that, I just want to show you what's presented here. This is hydrogen peroxide. You know, hydrogen peroxide, 3% solution, something that you can buy in grocery stores, you can buy it in pharmacies. It is a disinfectant. So this hydrogen peroxide bottle, sits in your cupboard for months or years, and it ends up not doing anything. But you take it out and you pour it onto a wound, and what it ends up doing is it ends up starting to bubble almost instantly. And that bubbling is the reaction to destroy whatever happens to be living there. So it actually isn't bacteria that catalyze the decomposition of hydrogen peroxide. That decomposition is actually catalyzed by the iron in your blood. So, and what ends up happening is that the decomposition causes a few layers of your skin, plus any bacteria that happen to be on the surface, to get their cell walls disrupted and therefore killing them. You lose a few layers of your skin, but what comes out of it on a positive sense is that any bacteria that was there have been killed as well. Over on here on the right-hand side, I've got a few other chemicals, and I think I probably should have put on all the PPE to begin with. There's a few chemicals that I really don't like to work with, and one of them is hydrogen peroxide. Not the 3% hydrogen peroxide that's right here. I actually had to use some last week when I burned myself, so I've used that on a regular basis. What I don't like is the more concentrated hydrogen peroxide, and in this case, this is 35% hydrogen peroxide. When you get 35% hydrogen peroxide on your skin, remember 3% eats away a few layers of it, and then the process, kind of kills bacteria. This actually does a good job of burning right through your skin. It leaves a little, if you don't get it off, it just reacts away and does a good job of burning through your skin. So there's some there, and the green color is due to some detergent that I've added for the purposes of this demonstration. Other thing I'm doing over here is I'm adding some of a catalyst to this beaker, and I need to add a little water to it as well, just to dissolve it out. So that's going to take a few seconds to dissolve. Now, if we had a class going on here, I wouldn't need to use this because I would just have a knife and ask for a student to volunteer. That was a joke, just pointing that out. Anyway, but iron, blood is not the only thing that catalyzes the decomposition. This happens to be potassium iodide, and the iodide ion also catalyzes this decomposition. And what we can see here is that the hydrogen peroxide in this graduated cylinder is sitting there doing nothing. There's around about 125 milliliters of hydrogen peroxide in the grad cylinder. What we're going to see is try to get an idea of how much oxygen gas, what volume of oxygen gas comes out of this during this decomposition. So after I add the catalyst, excuse me, need to get to the side. And then, because I don't want to get it on the bench top, here we go. Basically what comes out of it, that is easily 15, 20 times the volume. The other thing is you can see steam, you might be able to say steam coming off the top of it. It is a very exothermic chemical reaction. I'll let you watch that while I take off some PPE and go and return to the front. So we're going to look at that reaction right here. So catalysis introduces a new reaction to chemical systems. And that reaction here, as we can see, iodide is now present as a reactant. It needs to be there. And so in this two-step mechanism, we have hydrogen peroxide reacting with iodide to produce water and IO minus. IO minus is an intermediate again. And that intermediate reacts with another hydrogen peroxide molecule to produce water and oxygen gas. And critical to catalysis is it regenerates the catalyst. So iodide is consumed in one reaction and produced as a product in another one. If you look at the overall reaction, hydrogen peroxide decomposes to water and oxygen, you end up, that's better. You end up not seeing the iodide, which could equally have been iron or one of the many other things that catalyze the decomposition, and you don't see the intermediate in the overall reaction. They end up canceling each other out. So now we're going to sketch the reaction coordinate of the iodide catalyzed decomposition of hydrogen peroxide. What's shown here is slightly different form, but the reactants to hydrogen peroxide plus iodide has an energy of minus 438. Then there's the activation energy for the first reaction. There's the energy of the intermediate products. And the final products, water, oxygen, and iodide, have another energy as presented there. So now let's go and sketch this. Good. So this is the catalytic decomposition of hydrogen peroxide. Oops. The horizontal axis is just our reaction coordinate. And the vertical axis is energy in kilojoules. Looking at the numbers, it goes from about minus 400 to minus 650. Minus 650, minus 600, 5, minus 400. So that puts values on the axes. And then one needs to look at what we have. Our reactants have an energy of minus 438. And that was 2H2O2 plus iodide. The second stage had an action energy of minus 585. And we had a leftover hydrogen peroxide plus water plus IO minus. And final was at 627. And here the reaction had converted into 2H2O2, or sorry, 2 waters, plus regenerating the catalyst iodide, plus producing oxygen gas. Looking at the activation energy, the first activation energy is 50 kilojoules per mole, so that takes it up to 56. And my hand is getting in the way here, sorry. Takes it up to about right there. Oops, gets into my title. And the second one is small. It's not well known, so it's just a very small value. So one can draw the reaction coordinate goes up to the activation energy and then down, like that. This is 56 kilojoules, and this was small. Anyone have any questions on that? So what we were able to show there is the reaction profile for another reaction. As I mentioned in the last one, there was 2 things obvious that catalyzed the decomposition of hydrogen peroxide. One was iodide, the other is blood, iron in your blood. This is the decomposition, catalytic decomposition of ozone, in which case there are many entities that decompose ozone. So as presented here in the reaction, it's just Y, but Y could be anything from including atomic fluorine, atomic chlorine, atomic bromine, atomic iodine, nitrogen monoxide, hydroxyl radical, and sulfur dioxide. Any one of those can be substituted for Y and catalyze this reaction. The figure below uses chlorine. And in that case, you have chlorine plus ozone on the right-hand side produces the intermediate ClO. So ClO is one of the intermediate, or YO in the mechanism is one of those intermediates. And then that intermediate reacts with another ozone molecule to produce YO2. And oxygen is given off. And then YO2 by itself is fairly unstable and decomposes to give you back your catalyst, Y, and another oxygen molecule. The catalyst is Y. It is consumed and then produced. The intermediates are YO and YO2, but they all cancel out in the overall reaction of ozone is in two ozone molecules reacts to produce 3 oxygen molecules. So before I talk a little bit more about this, I just want to point out that in the atmosphere, ozone and oxygen are in equilibrium in the stratosphere. There is ozone that is, ultraviolet light from the sun is coming in and it is breaking apart oxygen. And that oxygen produces oxygen atoms which react with other molecules to produce ozone. So there is an equilibrium where you have ozone absorbing UV light and oxygen absorbing UV light, and you've reached a balance with a certain amount of ozone in the system. Actually, let's just go over here and do it. So the mechanism would be that of O3, it's actually in equilibrium, 3O2. So given that equilibrium, due to UV photolysis in the stratosphere, what we are doing by humanity putting in all of these radicals that can react with ozone is that we are shifting this reaction. This reaction is being shifted to the right-hand side. We are making more ways to deplete ozone and still have the same ways of creating ozone. So we're ultimately ended up shifting the equilibrium to favor oxygen. Once the entities we put up in the atmosphere come down, and the Montreal Protocol in the 1980s something or another, sorry, don't have the date off the top of my head, was the first protocol to decrease the use of CFCs, chlorofluorocarbons, in things like refrigerators, air conditioners, and the like. And in that last 30 years, what we have found is we can actually see a measurable building up of the ozone layer. But it's going to take hundreds of years to get back to where we were, because some of these entities, chlorine specifically, has a half-life in the stratosphere on the order of 100 years. So it will take a couple hundred years for it all, or the majority of it, to be precipitated out and the ozone layer to reestablish itself. Any questions? If we wanted to look at that decomposition directly, we end up with this profile right here. And looking at this figure, I think the activation energy is wrong for the uncatalyzed process. It says 374, but I'm fairly certain we did this earlier where we had it, when we looked at it here, we had numbers at 107 kilojoules for the decomposition to ozone. So I apologize, that number appears to be incorrect in here, but it is still considerably higher than the activation energy presented, which is 2.1 kilojoules. That's the catalyzed activation energy. And that produces the intermediates. The second activation energy is 33 kilojoules per mole, still many orders of, still a third of the 100 that we had before. And finally, to decompose ClO2, you end up with the reaction as presented here. Activation energy to break that bond of 16.7 kilojoules per mole. So this is the difference between the catalyzed mechanism and the uncatalyzed mechanism, which has an activation energy of about 107, not 374 kilojoules per mole. And yes, it proceeds through photolysis using ultraviolet light. So what can we do? We can do calculations using the Arrhenius equation. And what we want to do is we want to derive a combined rate constant equation now at a constant temperature, but varying the activation energy. Because that's what catalysts do. They vary the activation energy. We are making the assumption that the A parameter, the pre-exponential factor, is constant. I'm not going to say it's a good assumption, but it is a reasonable assumption, and it gives us values that we can work with. So we have the Arrhenius equation. K is equal to that. And when we are dealing with catalysis, we're going to vary the activation energy at a constant temperature. And we're going to make the assumption that A is constant. So we have A1 is equal to A2. Solving the Arrhenius equation for A and substituting it back in gives us K1 over that is equal to K2 over that. Rearranging this to give us K1 over K2, that is equal to, I need to move that down a little bit, K1 over K2 is going to be equal to E to the EA1 over RT divided by E to the minus EA2 over RT. And since we've already done this algebra, this simplification, I'm not going to go through it again. This is E to the minus EA1 over RT minus negative EA2 over RT. To simplify, we take the natural log of both sides. And this gives us natural log of K1 over K2 is equal to EA2 minus EA1 over RT. And this reaction is for catalytic systems. Where we want to determine how much faster a reaction is catalyzed versus uncatalyzed. Or the other way around, if we know how much faster it is, because we can measure that, that's an experimental observable, then we can actually go and calculate the activation energy, how much it has dropped as a result of the catalytic, the addition of the catalyst. Now we want to determine the increase in the reaction rate constant if the activation energy decreases from 50 to 45 kilojoules per mole at 295 Kelvin. So we have the equation that we're working with. And we have our two states. State 1, the activation energy is 50 kilojoules per mole. And we have K1 there. And state 2, the activation energy is 45 kilojoules per mole. And we have a value K2. Now, I arbitrarily set K1 or state 1 and state 2. If you want to reverse these two, if you want to make that state 2 and that state 1, you are free to do so. You'll find that you get the same answer. And that's important. It doesn't matter how we set up our states, you will get the same answer. So substituting all of this in, we have now this is why units are important. The activation energies are given in kilojoules. The value of R is in joules. So you should sit there and go, okay, I definitely need to convert to joules. 45 times 10 to the 3 joules per mole. And I'm just doing a conversion in my head. Hopefully you'll get to the point where you can do that without having to multiply by 1,000 joules per kilojoule. 50 times 10 to the 3 joules per mole. And all of that is divided by 8.314 joules per mole Kelvin times 295 Kelvin. So look at what cancels. Joules per mole is in every term, so it can cancel out. And then in the denominator, Kelvin is in both terms, so it cancels out as well. So that means this value is unitless. And so when we go through and do the math, you should get negative 2.04. In order to get rid of the natural log, we're going to take the exponential of this entire thing. And that gives us K1 over K2 is equal to 0.13. Or K1 is equal to 0.13 times K2. Or we could equally have rearranged it to get K2 is 7.7 times K1. So here, this is the answers we're looking for, and we're specifically interested in determining the increase in reaction rate. So how much faster is it, which makes this one the preferred answer. The reaction is 7.7 times faster if the activation energy drops from 50 to 45 kilojoules per mole. Are there any questions on that? How do you get 7.7 for K2? What you do in terms of getting 7.7 is you literally divide through by 1 over, multiply through by 1 over 0.13. Will give you 7.7. Okay. Why did we choose K2 and not K1? going back, so that's actually a good question. If we go back up here, I arbitrarily assigned 1 and 2, K1 and K2. K2 is going to be the faster reaction. Sorry, I'm going to let the system catch up. K2 is going to be the faster reaction because it has the lower activation energy. And I still have to let the tablet catch up. Give it just a second. Yeah, because K2 had the lower activation energy, K2 should be faster. And if I go down and look at the results, that's exactly what I see. K2 with the lower activation energy is 7.7 times faster than K1. If I had flipped K1 and K2, you would just flip K1 and K2 here, and you'd find out that K1 was 7.7 times faster than K2. Does that answer your question, Rafaro? Excellent. Good deal. Okay. So that is that information. To look at another catalytic cycle that is of relevance in the world, and that is catalytic converters in automobiles. Historically, two things. One, automobiles, older automobiles could be tuned such that you run fuel rich, fuel lean, and you got various different properties out of operating the engine. Now, if you Google things, what are they? Some trucks run super fuel rich and they rolling coal, they basically put out tons of black smoke because it's cool. That was one of the things that they wanted to avoid vehicles doing as they got out of engine alignment and didn't, So catalytic converters were introduced, and if there was an excess of fuel, okay, so you were running fuel rich, you had not enough oxygen, so instead of producing CO2, you might have produced carbon monoxide. And with excess fuel, you didn't burn all of the hydrocarbon, so you were left with some hydrocarbon, CXHY. The catalytic converter ended up converting the carbon monoxide to carbon dioxide, and it ended up burning the remaining hydrocarbon to CO2 and water. Those products are safe in the environment. Excess hydrocarbon is annoying. Carbon monoxide is what has killed people in homes with incomplete combustion. If you went the other way and you were running fuel lean, such that there was extra oxygen and not enough fuel, you actually had high temperature conditions where the oxygen and nitrogen gas would actually combine, and so this is nitrogen in the air, and you'd produce nitrogen monoxides. And so that same platinum palladium catalyst ended up converting nitrogen monoxides to nitrogen and oxygen, all on the same honeycomb structure as pictured below. So it did a great job of reducing harmful emissions from automobiles. The one problem was that prior to the 1970s, there's always sulfur in crude oil, and it just got passed on into the fuel. And so having a fraction of a percent of sulfur oxides, sulfur organics wasn't a big deal, except they poison catalytic converters. So a huge industrial push was done to come up with technologies to remove the sulfur from the fuel so that you didn't kill the catalytic converter. And that's so sulfur poisons the catalytic converter. It's an inhibitor of the catalyzed reaction. And now there's excess sulfur in the world, and people are actively looking for things to do with that sulfur. And there's actually projects or competitions out there to find things to do with quite literally mountains of sulfur in the world. All right, well, that actually concludes the material in the kinetics module. Going to have a couple pages of a summary here, and then we'll talk about next steps. So just as a reminder of the things that we covered throughout this module, kinetics is the study of the rates of chemical reactions. and we came up with a rate equation that allowed us to measure any reactant or product and still get the same rate. And that rate equation presented here is 1 over the stoichiometric coefficient times the change in concentration over change in time. The rate is affected by the concentration of the reactants, the state, and the temperature, and we saw that demonstration with the steel wool on the first day. It is also affected by the presence of a catalyst, and we saw that demonstration earlier today. The concentration dependence takes the form of the rate being equal to the rate constant K times the reactants and products raised to some arbitrary power, which is the order with respect to that reactant. Now, we really focused on reactants. We didn't focus on products. That gets another level of complexity. But that order of reaction indicates how the rate changes with respect to changing concentration. We looked at two different methods for determining the reaction order. The first one was the initial rates method. It's the most general because no matter what the order is, it will give you the value because you are taking the reactants as varying the concentration of the reactants and mixing them together and figuring out how fast the reaction is proceeding. And you do a number of runs by varying the concentrations of the reactants, and away you go. Secondly, you have the reaction profiling, and where we were limited by the orders tested, and we derived analytical rate equations for 0th, 1st, and 2nd order reactions. And we showed that by plotting what should be linear, we were able to figure out if it was 0th, 1st, or 2nd order. And finally, we looked at the temperature effect, how the temperature affects the rate constant, and that was given by the Arrhenius equation. This is also how activation energy affects the rate constant. But collision theory and transition state theory explain the Arrhenius equation, which was first postulated as an empirical function. And finally, we had the idea of a catalyst increases the reaction rate by providing an alternate, lower energy pathway, but is itself not consumed. And we also looked at mechanisms and elementary reactions. The overall reaction that you commonly see in textbooks is not what's occurring in the reactor. What you see occurring is, what you don't see is a whole bunch of more fundamental reactions where intermediates are produced and then intermediates are consumed, and all these elementary reactions add up to the overall reaction. But by knowing what those elementary reactions are, we are able to control the reaction. We can do things to make the reaction speed up or slow down. And the example I gave here was that by increasing the concentration of iodine radicals, we can increase the rate of reaction. And ladies and gentlemen, that actually concludes the Module 1 Chemical Kinetics units. Ta-da! What I want to say is that, okay, we're done this module, and actually I'm a day early. I wasn't sure how long it was going to take to go through this material because it is different than the material I've taught previously. So I estimated 7 days. It actually was done in 6. So on Wednesday, we are actually going to start equilibria, and the PowerPoint for the equilibria unit is available on Blackboard. So you can download and print that off and whatever you need to do there. But it also means that you have another problem set quiz. You have now all of the material for the kinetics unit, problem set 2, you can complete in its entirety, and you should be thinking about having a quiz starting on Sunday and going till Tuesday. So that gives you a week to do that. So that's where we're at. So to answer someone's question earlier, that's how I generally want to do the problem set quizzes, because I don't know exactly when we finish the material. So I will give you 5 to 6 days in this case, and then I'll set the quiz. Does anyone have any questions? Okay, the question is, what is the format of the problem set quiz? It is multiple choice. You will be asked questions literally off the problem set, but the answers will be a multiple choice selection. So if you've done the problem set, it's a matter of just looking back at your notes and going, oh yeah, that's how this one's done, and plug different numbers into it. How many questions on the quiz? I actually had to go look, and it's 3. And you have 45 minutes to do it, which is, if you've done the problem set, no problem at all. If you haven't done the problem set, you probably won't finish it. There is no graph simply because I have to mark that manually, and the problem sets are done. The problem sets are managed, all automated. So, any question? I hope that answers your question. I'm just going to stop the recording, and then I can continue answering questions.